We are Atlas Air Transportation, a multidisciplinary team of engineering and business students from South Dakota State University. Our sponsor is NASA and the SDSU Art Lab, and our goal is to create a multi-rotor drone that has enough lifting capacity to carry a human. We will do this through a rigorous design, build, and test process and aim to have the system operational in the near future.
Currently, we are finalizing the construction of Albatross, our large-scale drone. If all goes well, we should be up and flying within the next month. Our goal is to be able to carry a single person, or approximately 100 kilograms. Should we accomplish this goal, we will move on to the development of flying autonomously over short ranges and determine all the other potentials this project has to offer.
The Atlas team was created for the NASA University Student Research Challenge, or NASA USRC. As of March 2020, we are one of 4 teams selected by NASA to receive an $80,000 grant to pursue our proposed idea. However, there were some strings attached to this grant, one of which was that we had to run a successful crowdfunding campaign in order to receive the whole amount. I'm glad to say that we were able to meet this requirement and can give our full attention to the project.
We began our project by proving our concept of Albatross by developing a small-scale prototype that we like to call Hummingbird. This prototype's intention was to confirm our abilities to make an octocopter, as well as be able to test autonomous flight prior to running autonomous flight on Albatross. Through our experience designing, building, and flying the Hummingbird, we were able to develop new ways of improving the development and creation of Albatross. Currently, we have achieved manual flight with Hummingbird. However, we still have some work to do before we have perfected autonomous flight, so we can begin flying Albatross.
Now, the overall layout of the Albatross vehicle is that of an octocopter. Think of a standard drone that you can get at a store like Walmart. It's just like that, except it has twice the number of motors and propellers, and is about 8 feet tall and 12 feet wide. The Albatross vehicle will have a weight of roughly 150 kilograms, meaning that it will have to lift at least 250 kilograms when loaded. Now, obviously, the Albatross is able to lift more than that for safety reasons, but that is the minimum requirement of the system.
Our design has been extensively tested in many simulated scenarios, ranging from weld integrity tests to static strength at full throttle capacity. Through these simulations, we are confident that our design will be able to handle the maximum load capacity with strength to spare.
Progress on Albatross structurally is completed. Currently, the drone has a dry weight of 140 pounds or 64 kilograms. With the power that we expect from our motor selections, this is a great place to be at in terms of our takeoff weight. Key areas in our design to figure out the lightest and best landing gear and the safest and strongest ways to connect the arms of our hashtag structure. For this, we decided a solid structure for the landing gear connected to the cabin with 4 high-strength springs, and for the arms, we decided on gusset plates to add strength and stability.
We chose our 8-motor layout based on the system we were going to use to control the vehicle. This system restricted us to a maximum of 8 outputs or motors. Therefore, knowing that we had a lot to lift, we decided to use the maximum number of motors that we could. As for the motor and propeller pairings, we selected them so that the vehicle would hover, the flying version of idling, at a desired speed. We also had to select batteries so that we could link them together to get the desired power and capacity for liftoff and flight.
The number of rotors we also chose was cost effective. Given our approximate budget for propulsion, if we would have switched to 12 rotors, that would have severely limited our flight time. There are diminishing returns with adding more batteries to improve flight time, so we had to calculate exactly how much batteries we could get in order to maintain our thrust-to-weight ratio of 1.5.
Our control system uses the Pixhawk Cube and the Here2 GPS module, some of the best control systems on the market. Our ground control station runs Q Ground Control, a program that can be easily run off a PC or tablet, allowing for easy integration for a user interface into Albatross. Our goal is to have a permanent user interface incorporated into Albatross.
Of the total $82,000 that this project has been granted, $54,000 has been allocated to the supplies and project operations. Although the project is currently under budget due to delays in the purchasing of certain components, we believe that more funding may be required to truly achieve our goals. This funding could be used by a future student group to further improve the design and operation of Albatross through the addition of an enclosed cabin, increased battery capacity for increased flight time, or simply to refine the system design. Thank you for your support and interest in this project as we continue to achieve our milestone goals.